Okay. So we have 2 hours now, so it's 10 past 1, yeah. Right, so we're continuing where we left off yesterday. So where we left off yesterday is we wrote down the definition for the entanglement associated with an interval for a 2-dimensional CFT in the vacuum state. This is what we're going to try to calculate. It will take us some time. And in this definition, there's an object, z of n, that we understood we can make sense of for positive integer n. And we understood then that this is a path integral over some complicated surface called the replica manifold. So we understand it's a path integral. What we haven't done yet is actually calculate this path integral. So this is what we'll have to do, calculate that path integral. Then with this result, we can plug it into the definition S, and that's the strategy that we'll follow. But before we continue with actually calculating z of n, I want to go over some basics of conformal field theory, just to get everyone on the same level. I'll only explain the things that we will actually need or use, so it won't be a whole CFT lecture. But I want to introduce some things, particularly focus on the things that we'll have to use. Okay. So let's start with some definitions. So let's start with the definition for a conformal transformation. So a conformal transformation is a coordinate transformation. So taking your coordinates x to x prime. It's a coordinate transformation that leaves the metric invariant up to a scale factor. Up to a scale factor, and so this will be the case if this psi satisfies the conformal killing equation. So if psi satisfies the conformal killing equation, so which is roughly this. Okay, the point is that in 2D, so we'll be working in 2-dimensional CFT. In 2D CFT, it's clear that any holomorphic transformation of your coordinates will have this property that it leaves your metric invariant up to scale factor. Because your metric in 2 dimensions in complex coordinates is just dz, dz bar. And if you do a holomorphic transformation, meaning you take z to a function of only z, not z bar, then your metric will be transformed into some scale factor df over dz squared times dz, dz bar, okay? So this means that any holomorphic transformation in 2D is a conformal transformation, and the scale factor that appears in the metric under this coordinate transformation, typically you call big omega, and this is your scale factor or your Weil factor, okay? Good. So there's a special subset of all these 2-dimensional conformal transformations, which are the so-called global conformal transformations. Which are just the Möbius transformations, okay? So these types of transformations where A, B, C, D are complex numbers with the determinant of the ABCD matrix being 1. So these are called the Möbius transformations, and they form an SL2C over Z2 group. Okay, because with each transformation there's a 2 by 2 matrix with complex numbers A, B, C, D associated. And the over Z2 here is just because you can take each of these letters to minus themselves, A2 minus A, B2 minus B, etc. You'd still have the same transformation, okay? So this is a subset called the global conformal transformations, and physically the types of transformations that they describe are translations, Lorentz transformations, so rotations and boosts, scale transformations, and something called special conformal transformations. And so in higher than 2 dimensions, these are the only conformal transformations that you have. In 2-dimensional CFT, you have infinitely more conformal transformations, namely all these. Okay? And then these global ones form a special subset. Right, then, so this is the definition of conformal transformation. What's the definition of a CFT? So a CFT is a quantum field theory that has conformal invariance, which can be expressed in terms of the correlation functions. So namely that the correlation function of the operators remains invariant under a conformal transformation that changes the operator from O to O prime. Okay, so I have an operator in one point and then a bunch of other operators in other points. So this is just a general notation for a general correlator that is conformal invariant in a CFT. Okay, so this is the same way that you would express Poincare invariance of QFTs. So a QFT with some fixed Minkowski background can inherit the symmetries of that Minkowski geometry, namely translations and Lorentz transformations, or together they're called the Poincare transformations. And if it does, then its correlation functions will be invariant under those Poincare transformations. So for a Poincare invariant QFT, this statement about the correlators will be true, but only for the Poincare transformations, which is a subset of the conformal transformations. Namely, it's just these ones, okay? And so in a conformally invariant QFT or CFT, this statement will be true for all conformal transformations, so also including scale and special conformal transformations, and in the case of 2D CFT, all these holomorphic transformations. Okay, I'm going to call this 1 for one way of expressing the conformal invariance of correlators in CFT, because we'll write down a second one, which is the one that we'll use most in a bit. Okay? Actually, what I'll call 1 is actually the next line, which is the same equation, but making something explicit that I have not made explicit in this line. Which is that we're talking about correlators of a quantum field theory, namely this conformal field theory, defined on a background metric ds squared. And so if you write down a correlator, you're comparing operators at some position x1 and then other operators at other positions. So you're implicitly already assuming that you have this background metric. But you wouldn't actually include this in the notation usually. But there's a reason why I do this now. Okay. This is what I call the first of two ways in which we'll write the conformal invariance of correlators. Okay, now, the structure of CFTs is such that the operators can be classified in terms of a special class of operators called primaries. Primaries are basically operators that you cannot write as derivatives of other local operators. Called primaries, but I'm going to add in brackets Vera Zorro. I'll explain why. Okay, called primaries. So we'll use this concept, so I have to tell you what a primary operator is. Again, so actually a Vera Zorro primary operator, because I'm interested in 2D. The way you define what a primary operator is by saying how it transforms under conformal transformation. So we understand now what are the conformal transformations. Primaries are operators that transform as follows. Bar. Okay, so they are operators O in some point Z, Z bar. And under conformal transformation, they transform with these two factors. So you see that there's two parameters appearing here, an H and an H bar. These are called the conformal weights of a primary operator. So if you want, you could label a primary operator by their H and H bar. But okay, it's a bit of a heavy notation, so we don't do that. But a primary operator has an H and an H bar. So let's not use this notation, but we know that it has these conformal weights. So it has conformal weights, or it means that it has what is called the scaling dimension delta, which is the sum of those conformal weights, and a spin S, which is the difference of those conformal weights. So let me write in the case of operators which have zero spin, and so equal conformal weights H and H bar, then I can write this transformation behavior in terms of the scale factor omega associated with the conformal transformation. So let me do that. So then I have dz prime dz to the minus 2h o zz bar, which I can write as omega to the minus h o z z bar. Okay. Fine. So for some people, this is all repetition, so I'm trying to go a bit faster. Okay, but you'll notice now that I've given you the definition of a primary operator. So I'll call it primary. Depending on which dimension CFT you're in, a primary refers to an object that transforms in a certain way under the conformal transformations. So in higher dimensions, that would be just under the global conformal transformations. And in 2D, that would be all the conformal transformations. So you have to distinguish between primaries and two-dimensional primaries. And that you do by calling the two-dimensional ones Virasoro primaries. But I will just use the word primary. This is just a comment, but for us it's fine to call it primary because we will only talk about 2D CFT. Okay. So there's no ambiguity. So you'll notice that the definition of the primary operator I've given to you in this form. So I've told you how its primary operator is an operator O of x that transforms under conformal transformations as such to some O prime of x prime. Okay, you'll see that in the statement of conformal invariance of correlators, what I have here is not O prime of x prime, but O prime of x. Okay, so what is O prime of x for this primary, for example? Okay, so the difference here is between what is called a passive conformal transformation or coordinate transformation and an active one. Okay, and this can be a bit confusing, but it will lead to the second version of writing down conformal invariance of correlators. So there's a difference between what is called passive transformation, in which case you write the transformed operator as O prime of x prime, and an active transformation, in which case you write the transformed operator as O prime in x. Okay, so what's the difference? So passive is a transformation. The difference between passive and active is the difference between two possible interpretations of your conformal transformation to x prime. Okay, so the passive one is interpreting this coordinate transformation just as going to a different frame of reference. So looking at all of the physics just from the point of view of a different observer. That would lead to an O prime of x prime, okay? An active transformation is basically what you get when you act with the generator of this conformal transformation on the field. And this active transformation interprets this coordinate transformation in a different way. It doesn't interpret it as just going to a different frame of reference, but instead you interpret this transformation here as taking the point that is labeled as x, actually physically moving that point on your manifold in the direction of the vector fields psi mu, and then relabeling, so then at that point actually doing a passive coordinate transformation to relabel the new point to have again the same value x as coordinates. So in an active coordinate transformation, the procedure that I just told you in words just takes x back to x. But you've done a physical transformation because you first moved the point and then did a relabeling. But mathematically speaking, this is why there's just an x here, not an x prime. compared to for the passive transformation. So we'll say a bit more about this in the exercises. But just understanding this difference between passive and active allows you to write down O prime of x if you know O prime of x prime by a trick, which is the following. So O prime of x prime for a primary is dx prime dx to the minus, well, delta, let's say, O of x. And then the active one is this. So the trick to get the active form of the transformation is that you can effectively swap the roles of x prime and x. So let's see if I did it right. I think so. Why this is true, this rule, is something that we can discuss in the exercises with an example. Okay. But it helps to know this rule. Good. Sorry?
Is this only for h equals h bar, this last transformation you're at?
Well, it's supposed to be the higher dimensional version in which delta is just h plus h bar. But the way I wrote it before, it would be yes for the special case h equals h bar. Let me erase part of this board that I don't have to change the. Well, so we don't really need this. Good. So now we can ask, can we write this statement of conformal invariance of the correlation functions? Can we write that instead of in terms of this active transformation, which is a bit tricky to interpret with the x prime and the x switched? Can we instead just write down a second version of this statement, but in terms not of the O prime of x, but in terms of O prime of x prime, so the passively transformed fields? And so I'm just going to give you the result. And I'll call it 2 for the second way we can write this conformal invariance. Okay, so the statement is that I don't know how to say this statement in words, but the correlator for the CFT on ds squared with passively transformed fields equals the correlator on a conformally related manifold with a Weil factor omega that's associated with the conformal transformation here to O prime of the O of x operators. And so now it's clear why here I went through the trouble of actually adding ds squared there. Because here you're relating correlators with a different background metric, but conformally related background metrics. Okay. And it's the second version of conformal invariance of the correlators that we will heavily use. Okay. And so when I say things like the CFT does not care about Weil factors in the metric, this is really the statement that I mean, is that there's this form of invariance. Okay. So it's, for example, typically what you use to find the stress tensor of a 2D CFT on a cylinder from knowing the stress tensor on the plane, where the plane and the cylinder are conformally related metrics. And this is a typical thing that you do. But really what you're using is this form of the correlator invariance. So there's, Tom Hartman has some notes on this called 2' or not 2'. And that actually derives this form. So to summarize, we've written down two equivalent statements of conformal invariance. One is the natural one to express conformal invariance of a CFT, which has a fixed background metric. And the second one is useful in calculations to conformally map your problem to a different background geometry which is conformally related. So this all comes from the fact that I started with a definition, so it's still there, of conformal transformations as a type of coordinate transformations which leave the metric invariant, so saying something about how this transformation acts on the metric. But then in a CFT, you have a background metric which you keep fixed, so that can be a bit confusing. And that's why I write down those two equivalent statements. Right. Let me write two in one more form using the writing out the transformation of this first operator that appears as omega to the minus h of x1 in ds squared is O of x1 dot 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 omega ds squared. Okay, so this is 2', let's say. Which is the one I'll actually refer back to. When we use it, I'll let you know. Okay, this is a bit of a long title for the next page. But talking about whether or not to consider the conformally transformed metric, which has to do with thinking about passive or active transformations. That brings me to another subtle point, which is the following. And once the end point of this will be the starting point for our actual calculation. So the next subtle point is the expression of change in the action under an infinitesimal coordinate transformation in terms of the stress tensor of the CFT. Okay. So let me first make a statement about matter action in the context of gravity. We're not talking about gravity right now, but there's a reason why I bring it up. Say that we have some matter action coupled to gravity. Then the matter stress tensor is defined as follows. It's defined from how the matter action transforms under metric transformations. So the sign here is important. Okay, so you know that this is a stress tensor definition in GR for the matter section of your theory. So you get it from the differentiation of your matter action with respect to the metric. So the first line is just a rewriting of the second line, right? Actually, let me add one more thing, one more way of writing the first line with the opposite sign, because this can also be a confusing sign. Okay. So if you write it in terms of the stress tensor with the indices up, then there's a sign disappearing here, which is because the derivative of the inverse metric comes with a sign with respect to the derivative of the metric. Good, so this is one source of sign confusion when you see formulas like this. The other is what we'll explain next. Okay, so now let's go back to our QFT action. And let's ask, how does my QFT action transform under general coordinate transformation? So general coordinate transformation delta x mu. So it's what I have called psi before, the change between x prime and x. All right. So this is a QFT, so there's no reason why under general conformal transformation this would be 0. So it will be equal to something. But what is that something? Okay. So the trick you can use is that you know that if this QFT was coupled to gravity and its metric was actually dynamical, then that would be a matter action coupled, a matter action of a full gravity theory, which is invariant under general coordinate transformations. Okay, so we know, the trick is that we know that if the metric of the QFT would actually be dynamical, then under the coordinate transformation, the action would actually be invariant. So by general coordinate invariance of gravity. Yes?
What do you mean by general coordinate invariance? Because I mean, I can write down an action in an independent way and it's invariant under all coordinate transformations.
Right, but this again has to do with this passive versus active. So people make the statement that GR is a diff-invariant theory. So is another way of saying that is that GR is invariant under active coordinate transformations. And this is what I mean by this general coordinate invariance. Okay. General coordinate, so that type of active coordinate invariance and passive coordinate, what you are talking about is passive coordinate invariance. So for example, passive coordinate under passive coordinate transformation, also your metric will change because it's just a change in frame of reference. So for example, my metric can change from dx squared plus dy squared to dr squared plus r squared d theta squared in polar coordinates. But it's actually the same metric. In an active point of view, your dynamical fields can change because you're moving your points. So it's a more physical way of describing these transformations. In that picture, your dynamical fields will change, but your background fields will not. And this is why if you have a QFT coupled to gravity, the whole thing is invariant under all types of psi's. Okay, this is general coordinate invariance. But then when you fix this metric, all that is left of all that invariance is only the killing vectors that leave that background metric invariant. So this is the difference between the statement of general coordinate invariance in gravity being a special thing compared to the type of passive coordinate invariance that you have in mind. Right, sometimes the more words you say about this, the more confusing it gets, but I don't know if it helped.
No, I think it's okay. Yeah, thank you.
Yeah. I'm just thinking if I should add something to it. Yeah, no, let me not, but. Right, so the argument was the following, that if we imagine that this QFT was defined on a metric that's actually also allowed to transform along under the coordinate transformation, then we would have that the whole transformation leaves the action invariant. And the effect of a coordinate transformation on the metric is written like this. Okay, so this you can check for yourself from the tensor transformation of a metric. This is the way the metric transforms. So you shouldn't take this notation that I'm using here too serious. It's just to write some formulas instead of saying these things in words, okay? But from this trick, we deduced that the transformation of the QFT action under the coordinate transformation is equal to minus the change in the action, as if its metric is dynamical under just a metric transformation of this form then, okay? So it's equal, because of the stress tensor definition, to plus a half T mu n delta G mu. Okay, let me not write the determinant of the metric because I've been assuming that the background metric is flat. Okay. Okay, so I can write that as T mu nu m d mu psi nu, or as a half, no half, T mu nu d mu psi nu. Okay, so now we've written down how an action, a QFT action transforms under coordinate transformation. So in this last step, I've just removed the GR notation with M denoting the matter part. So T mu nu is now just the stress tensor of my QFT, and psi is my delta x. Okay. So now we have what is written there as the title. We have the expression of the change in the action under an infinitesimal coordinate transformation in terms of the stress tensor. Okay. Next. So, well, the point was to emphasize here this confusing sign, which you'll see in every kind of way. This argument with the sign is also what appears in the derivation of the Schrödinger equation for the wave function as a path integral that I wrote down yesterday. So I refer to this paper by Halsey. Larson and Wilczek. And so that page where they do this derivation also makes use of this exact same argument that we just went over, okay? Actually, I could leave this and then say expression of change in Z. Okay, so we know how the action changes. Now we can look at how the Euclidean path integral changes of my QFT, and I'm interested particularly in CFTs. Okay, so I just have to write out this line. Okay, so I'm wondering how my Euclidean path integral will transform under coordinate transformation. I know how the action transforms. I've just included a 1 over 2 pi because that's a convention in 2D CFT. Just so for the definition of a stress tensor. And so the log of z will vary as delta z over z. I write out what delta z is. So this is minus delta I. And delta I I've written here. So it's minus 1 over 2 pi. The expectation value of t mu nu, but the normalized one, because I have a 1 over z here. Of course, I won't always write this, but there's a point in the calculation where it's good to remember that it's the normalized one, d mu psi nu. So let me write delta log z So now I drop that it's the normalized one, d mu psi nu d2x. It's basically the previous line, but written in terms of psi nu up, which is the one I know from how my coordinates will transform. And this is now the starting point of the calculation of the object z of n, which is this n-fold replicated Euclidean path integral. So this thing will apply generally. So it applies to delta log z of 1 for the theory that we wrote as the Lagrangian for fields with xte in the complex plane. And it will apply also to log zn. Sorry, this is probably, is this readable or not so much? Sorry? Okay. So delta log zn for when we consider the Lagrangian on this complicated surface, okay, with xte now running over the replica manifold. Okay. Okay, so this boxed statement is the starting point for the replica manifold derivation of the entanglement entropy. And this is probably a good time to take a break so that we're sort of back on the original schedule. Right? Or no? Because originally I was supposed to start at 1, no? So let's do 10 minutes break now. And then meet again 12 past, quarter past. Or, yeah, just before. Okay, so I'll start again. No, actually, it's on. Good, so I'll start again. So as I said, we ended with the starting point for the replica manifold derivation of the entropy. So let's consider our theory on this replica manifold. And if you remember from yesterday, this is this special manifold that is everywhere flat except at those two special points where there are conical singularities. So that was the characteristic of this manifold. Everywhere flat except at the branch points, VA is x1, x2. Okay. So let me repeat the starting point, the change of my Euclidean path integral under a coordinate transformation is given in terms of the stress tensor of the CFT on this replica manifold as such. Okay? So this is under a coordinate transformation x to x prime, like so. Okay, so why is this the starting point? Because if you remember, what I want to calculate is this z of n. Okay, so what's the strategy is going to be that we are going to consider a particular coordinate transformation that induces a change in the length of our interval. So in the distance x2 minus x1 of our interval A. Then we'll use this formula to find delta log z over delta L, which we can then integrate to find log z of n as a function of the length of this interval. Then we plug that into our definition for the entropy, and we'll find the entropy as a function of the length of the interval. This is a strategy that will follow. Okay. So first up is finding a coordinate transformation that induces a change in the length of my interval. And so I'm going to, so there's different choices, right? So nobody is restricting which coordinate transformation you choose here. And I'm going to use one that is actually not a conformal transformation. Most of the time people choose for this type of coordinate transformation, delta L inducing coordinate transformation, they choose a scale transformation, so conformal transformation. But I'm going to use a non-conformal transformation. Because this is this top line here is for any coordinate transformation, okay? So here I'm following a paper by Cardi from 08-07. It's called CFT and Statistical Mechanics, I think. So remember, I have my interval A. I'm going to try to consistently draw it in red. This is my interval A, so with endpoints x1 and x2. I'm going to pick an x0 that sits in between x1 and x2, so I'll put it right in the middle. And choose this coordinate transformation, which I'll just show in one line, okay, that this induces a change in L that is equal to delta L, because, okay, x2 minus x1 under this coordinate transformation will go to x2 prime minus x1 prime, which is x2 plus delta L for x2 because it's larger than x0, and x1 remains the same because it's smaller than x0. So I have L plus delta L. Okay. Okay, this is just to convince you that this is a coordinate transformation that does what I said it would do. And now let's apply, let's apply the top formula. So we have that delta log Cn So I'm only changing my x-coordinate of my two coordinates, x and time. So I have xi, x up there. That depends only on x again, not on t. So I have a dx of psi x, and therefore it picks out the x component of t. My psi is a theta function times delta L. So we'll just work that out. We'll have txx, then the derivative on the theta function gives me a delta function in x is x0, dx dt. Okay, what I've done in this step is just in this last step, I just do the integration over x. So my stress tensor is now evaluated in the point x is x0. And at this point, it's also safe to bring down this upper x because in x0, this background is flat. I don't know if there's a stick. But this geometry upstairs is like I said. The theory we're considering is our Lagrangian defined on this replica manifold. That replica manifold is everywhere flat except at these points x1 and x2. So x and te, they span the full replica manifold. And in these points, there are conical singularities, but in x0, the metric is just flat. And so, it's safe to bring down this x. Okay. Okay, so I have to integrate over all of the times. So I would integrate. Let's do a color. So my integration range is all of Euclidean time. So I'll draw the picture again. So I have x, te, I have x1, x2, and an x0 in the middle. And I'm integrating over all of time here at x0. So, okay, like this. So the blue is my integration contour. So now to work this out, what I'll do is I'll go to complex coordinates. So I'm going to use zeta as my x plus I te. So this is now the zeta plane. And I'm going to rewrite this integral in terms of my complex coordinates. So let's do like this. We'll go to complex coordinates. Zeta is x plus I te. Zeta bar is x minus I te. And then this will become minus delta L. d zeta 2 pi I. So this is like d zeta minus d zeta bar over 2. Okay, so if you just go to complex coordinates, this is what you'll find. Where I've changed the contour by doing a contour deformation. So this is a notation for contour around x1, okay? So what I can do is just I deform this contour to the circle around x1. I could have also chosen to deform it to be the circle around x2. That will not change anything. And so this zeta here, the dependence of t zeta zeta, this now has to be any zeta, not just x0, because it has to be the zeta that circles around x1, that follows this red circle. Okay. Okay, so let's go to this one. So now we just have to do this complex integral to work out this log Zn. But we need a trick to know what is this integrand of our complex integral. Namely, what is this expectation value of the zeta-zeta component of the stress tensor? Okay. So most of the time, I will not specify in which background metric we're considering the theory, as usually you don't in the notation for correlators. But let me remind you that we're working with the theory. So the setup there on the top of that board is our Lagrangian on the replica manifold. So I am looking for this object, okay? And the trick is to use that we know that the stress tensor expectation value vanishes on the plane. So we can do these typical tricks of finding a conformal mapping that takes us from the plane to this replica surface in this case. And and use the transformation law of the stress tensor to find this object that we're looking for. Okay. Oui. Yes, question?
Is it clear that something like this exists? Like this control?
Well, I will write it down, so yes. Well, so actually, the mapping I want is zeta to z because, okay, let's start from zeta. Should I take a break for the... So I'll do conformal transformation in 2 steps. This is now my geometry. So yesterday I was writing this replica manifold as this complicated figure with n copies. Now I'm pushing all these n copies into one plane. So zeta runs over the whole replica manifold. So I'm imagining that all of that information is just in the plane. The way it's in the plane is just that we have to remember what we discussed yesterday, which is that there's 2 special points in this manifold where it takes you 2 pi n to go around. Okay. So first, let's do a conformal mapping, which maps the left point of the interval to the origin and the right point to infinity. So our interval becomes the half-line, infinite half-line, instead of the finite interval. So I have my left point at 0, the other one at infinity. Let me call this coordinate now W. Okay. W. So the mapping that I do is I take zeta to zeta minus x1 to map x1 to 0, and I divide by x2 minus zeta so that x2 is mapped to infinity. Okay. This is the mapping I do, and I call this new coordinate W. I haven't done anything special, so my angle here is still 2 pi n. Okay. Now next, I want to map it to the plane. This is infinity. Okay. So to map it to the plane, I take my coordinate that I call W, and I take it to the 1 over nth power to basically orbifold this replica manifold. So the replica manifold, because it's created as these n copies that are cyclically connected, has a Zn symmetry. If you mod out that Zn symmetry, you just get what is left on one copy. So modding out or quotienting over Zn means that you identify points in your geometry that are the same up to a Zn transformation. Zn transformation being one that takes you to the next sheet. Okay. So the way to do that mathematically is go to a new coordinate, which is the 1 over nth power of this one. And you identify these lines. So this is now a sketch, which people sometimes call the pizza slice. Because I was squashing all of the replica manifold, all of the n copies, onto just one plane. Just a second, but with remembering that the full angle is 2 pi n. Because I started with this in the blackboard. just C is less than the full plane. It's a 1/nth of that. So this would be like, okay, I don't know, for n is 6 or so, that I'm drawing 1/6 of the replica manifold, being the plane then. So the point is that this angle is now 2 pi. It just doesn't look like 2 pi because I started from this angle that looks like 2 pi to be 2 pi n. Sorry, question?
So yeah, so this zeta is just a complex number for just one of the sheets. But there...
No, zeta here is in R and A.
Already, okay.
Yeah. Because I'm, the starting point is the theory on the replica manifold already. But okay, it inherits just the points x1 and x2 of the location of where A is. The replica manifold, like I said yesterday, I write this, but some people write Zn of A or something. So this object knows that there's an A. And that's why there's also an A in these pictures already, but this is in the replica manifold.
Okay.
Yeah.
So mathematically, is it just a... you cannot cover... Okay, can you cover the replica manifold with one chart? Or you do need multiple charts? And then...
Well, no, I can with the zeta.
Okay.
And that's what we do with the zeta. And right, all we need to know is that there's these sheets and that zeta jumps between these sheets.
I see.
Yeah. So zeta is the coordinate that yesterday we were implicitly discussing. Yeah. Okay, so this last step, or this last transformation that you do has a name. So you can call it Zn orbifolding or uniformizing. So finding a coordinate that brings you back to the complex plane is called uniformizing. And so in this case, that requires that you Zn orbifold. So these are just some words. Okay, and so now that we've found this conformal mapping, we still need to know how the stress tensor transforms under this conformal mapping, so that we can use this trick upstairs. The way it transforms is as follows. So let me first write it down and then how to find it, maybe. So if I would just write this would be a standard tensor transformation behavior of a mu object. But the stress tensor in 2D CFT has this extra part. So an anomalous transformation behavior, meaning that there's an extra term here where C is the central charge of your CFT. It has to do with the Weil anomaly. But you can forget about that if you don't know about it. And this object here is something called the Schwarzian derivative. So the Schwarzian derivative so this is just notation. This is notation for the third derivative over the first one minus 3/2 the second over the first derivative squared. All right. Okay, so what I'm writing down here is the passive transformation behavior of the stress tensor. The way to remember the passive transformation behavior of a tensor, for me it works best to think of GR, which is outside of this, the setup of this calculation again, okay? But for that one, you can remember dx mu rho sigma dx prime mu. For that one, you can remember how a two-tensor transforms because you want ds squared to be invariant. So here you see that ds squared on this side equals ds squared on this side. You see it? And that tells you the passive transformation behavior, so the g prime of x prime. And so for stress tensor, yeah, let's just change it. Here for stress tensor, this would be the same transformation behavior if it was just a tensor. But as I said, there's this anomalous term in the 2D CFT. Okay, so this you just have to accept for now. I cannot. So this is the passive transformation. You can also write it, let me just add it quickly. So sometimes you'll see the passive transformation behavior written in terms of the opposite Schwarzschild derivative, meaning the one of zeta with respect to z instead of z to zeta. And that rewriting uses the fact that z zeta is, well, I don't have it here. It's minus, okay, let me write it in the exercises what the inverse Schwarzschild is, okay. Zeta z, there's some d zeta dz squared and a minus sign, I think. Okay. But this is to be corrected in the next hour when I checked what it is. So let's forget about the second line for now. It's a common to point out a useful property of this Schwarzschild derivative. But I want to write down the right version, so let me do it in the exercises. Now what we need it for is to find the integrand over del log z by using the fact that the expectation value of t of z vanishes. Okay, and we have this number here left, which is the Schwarzschild derivative. Okay, so this is usually how you would see statements like this, but just added expectation values on the left and the right. But we can add in which matrix these expectation values are taken. So one is in C, where this vanishes, and one is in the replica manifold. So here, this is of this form of this boxed invariance of the correlators that I wrote down before. But with the change that the stress tensor has this extra transformation behavior that causes this extra term here, okay? So I'm adding this here to remember the structure that we discussed in the last lecture. So now we're ready to use this trick. We know that the stress tensor on the plane vanishes, the expectation value. This is just because of translation and rotation invariance. And then we're left with this simple statement that this expectation value is just equal to C over 12, the Schwarzschild derivative. And we can calculate this because we know the conformal map between zeta and z. Okay. So this is just a matter of actually performing all these derivatives. And if you do that, you'll find this result. Okay, so next we have to work, so now we know the integrand of our complex integrals. We just have to work out these complex integrals. The way you do that is by using residue theorems or Cauchy theorems. So let me write those down for you, the residue theorems. So the first one is this. Right, so everyone remembers the residue theorems. So the way to remember this is just the case where you just have dz over z, and you write that for a coordinate that z that is equal to e to the I theta, so that just makes a circle around the origin. So then you would write this as d log z, which is I d theta then, which is 2 pi I, okay? So therefore, dz over 2 pi I z would give you 1, and this is how you remember this formula. And then the next one that we need is the one with higher order poles. So this is a k plus 1. Is equal to faculty for k larger or equal than 0. The way to remember this one is just to remember the first one. So the first Cauchy integral formula, and then you path integrate. Sorry, not path integrate, partial integrate. Then you partially integrate. So you can always rewrite this one in terms of the first one by doing partial integration. That's why you have d to the k powers of derivatives here. Okay. And no signs left, so that's easy to remember. Now let's go to our complex integral. We have delta log Zn d zeta over 2 pi I x1 minus x2 squared over zeta minus x1 squared x2 minus zeta squared delta L This is C over 24, 1 minus 1 over n squared. Let me already add the times 2 here. I have two terms, one for the holomorphic stress tensor and one for the anti-holomorphic one. The anti-holomorphic one, basically from the same line but with the barred z. You'll see that it catches a sign, and therefore the minus the second term will contribute the same as the first term. So there's a times 2 because of the second term there. And so now we just have to work out this complex integral by writing this inner part, all of this. No. By writing this as f of zeta, okay, so f of zeta over zeta minus x1 squared. Okay. There's one subtlety in this, which is that it actually takes an angle 2 pi n to go around x1 and not 2 pi. So what I wrote here are the residue theorems on the complex plane, the standard residue theorems. But we are working on this complicated manifold, where actually this angle is not, the angle that you get in this derivation is not 2 pi, but 2 pi n. If you go, so let me write it in a different color. So applied to our complex integral with a contour that circles x1, the special point x1. F of zeta minus x1 is actually n times f of x1. Because, okay, this argument would tell you that d zeta over zeta is 2 pi n I. So there's an extra factor of n in this residue formula. So if you would just plug this in Mathematica and ask for the residue of this integral, you would get the right answer up to this factor n. Okay. So you have to remember what I added there in green. And so you can work out the residue on paper with those formulas, or you can ask Mathematica, and then you will find this following answer. So this is all this stuff that we're carrying along, and the residue is 2 over L times n. Okay. So as promised, this means that we have found delta log z over delta L, and it's equal to minus c over 6 n minus 1 over n over L. Plus dot dot dot, meaning these are L independent terms. And again, our whole discussion is for integer positive n, because we're working with a replica manifold, which only makes sense for a positive integer n. So this is our result. Now we just have to integrate this. So that will take me a couple more minutes, but I think that's fine, right?
Yeah, you get at least 10 minutes.
Ah, yeah, that's more than I need even. Yeah. So which one? Let's do this. Right. Thank you. Yeah. Okay, so we've arrived at an expression for the L dependence of our Z of n, which is the trace of the reduced density matrix to some power, for this power being an integer value. Now comes this analytic continuation argument, which I'm just going to give a sketch of. Okay, so we've found the formula for this Z of n. And the simplest thing to do is just to believe this formula, or this del log Z over del L, to believe this formula just for all n, not just for positive integer n. And this is actually the thing that you're allowed to do, because there is an argument why this is allowed. The full Z would be equal to the one that we've just found, plus some extra terms that you could have for alpha that is beyond integer n, which would be of this form: some sine functions times any analytic function. Okay. And it's been shown that this is actually 0. So there's a paper that I can refer you to by Solodukin, and he has an argument for this, based on the fact that the normalized reduced density matrix has eigenvalues between 0 and 1. And then he uses some theorem. So let me give you the reference. So this probably explained in many places, but this is the reference that I know by Solodukin. And then, so the result of that argument is, okay, you can just believe the expression that we found to hold even beyond positive integer n. And this is what we'll do. One reason why I'm not focusing too much on the mathematical explanation for why this analytic continuation is allowed is because when we get to the thermal entropy interpretation of this calculation, that interpretation will make it clear that there has to be some mathematical way of understanding that this analytic continuation is allowed, because from that point of view, it's clear that that has to work, okay? But so for now, we believe this argument, and so therefore, we believe this also for non-integer n. So we assume that there's a unique analytic continuation. And then we integrate that to this line, again, plus L independent terms. And now all that's left to do is plug this into the definition for the entropy. And we find this, this final result that the entropy is given by C/3 log L. Log L doesn't make sense by itself because the length is a dimension-full number. So we have to adjust this to include some scale in your theory. And this epsilon is the UV scale or the UV cutoff. And what it does is it regulates the infinite contributions that you receive to this entanglement from degrees of freedom that are infinitesimally close to the boundaries of your region A, so 2x1 and x2. So this is the final result. This is the famous log scaling of entanglement entropy in a two-dimensional CFT. And so it's a universal formula. For 2D CFT entanglement. Right. Is there anything else I need to mention now? Well, I don't think so. So, so this is a derivation in terms of the replica manifold. There's a second interpretation of what this Z of n is, and it involves twist fields and a replicated target space instead of a replicated world sheet. And so that calculation is by itself interesting and gives other insights, and that one we'll do next time. Because I ran out of time, right?
I think we still have time for questions if you still.
Okay.
Are there any questions?
Yeah, we neglected those 3 dots that are L-independent term, but once integrated, they can give something proportional to L. So what's the reason why we can just throw them away?
I didn't understand how the L-independent terms can contribute.
Well, we integrate this relation, right?
Ah.
So, I mean, once we integrate, I mean, constant integrate, we give something that is proportional to L.
Yeah, okay, I see. Right. Yeah, I'm not sure. So I should check. So this is I'm following the derivation from Cardi in this paper that I mentioned, 0807. And so I probably took that directly out of that paper, the statement that the rest are L-independent terms. Let me check if I wrote it in the right place. Yeah, I'm not sure.
Okay, thank you.
So let me maybe add one thing before the next question. Is no, that won't help with that.
You said that the stress tensor vanishes on the complex plane. You said that the stress tensor vanishes on the complex plane, the expectation value of the stress tensor. But shouldn't it generally vanish on like the flat complex plane or in coordinates where it's flat?
Right, exactly.
So those were flat coordinates. Like if you do the coordinate change, they'll still be.
So the whole point of the mapping, so it's not on the board anymore, but the whole point of the mapping is that you go from zeta coordinates that run over this complicated manifold, the replica manifold, to z coordinates that run over the complex plane, the vanilla complex plane.
Yeah, so I mean, I guess my confusion is just, I don't understand. I understand how it can get rid of the conical singularity part. The mapping will get rid of the conical singularity. But then away from the conical singularity, my impression from the coordinate transformation is that the metric will be still flat physically, but kind of non-trivial away from...
No,
no,
the
it'll
replica
be
manifold is it's flat everywhere except in these special points. And so once you've done these conformal transformations, what you end up with is in fact just a complex plane. So what you're asking is whether Rna over Zn, you're asking about this, whether this is true, and this is true. So, and this one is spanned by Z, this one by zeta.
Yeah, I think maybe I'm using, I'm mincing my language or something. What I mean is like if you have dz bar and you're on the complex plane, and then you do a conformal transformation, you would expect that your stress tensor would pick up the Schwarzian part, right? This extra piece.
Yes.
Right. So if you do this transformation that you wrote down on the board, which takes you from RNA, you know, to from the replica manifold to C, will you have the metric look like dz, like ds squared equals dz bar? It'll like look like that in those coordinates, or will it, you know, or will the?
You're asking about So I'm still not sure, completely sure I understand your question, but let me say one thing. So ds squared is dz bar in C. If you do the z to w transformation, this will be some factor dw bar. This will be some factor d zeta bar, with different y factors at every point, right? And then, so the statement is that dz bar is C, and d zeta bar is RNA.
Okay, I think.
And so you drop these conformal factors, or CFT doesn't care about these conformal factors. Is again using this form of what I called 2' of coordinate invariance of the correlators.
Right. Okay.
So the O prime of the x prime in ds squared, and the O of x in omega ds squared. So it will tell you how expectation values in the replica manifold are related to expectation values in the complex.
Yeah. Okay. I think that answers my question more or less.
Yes.
Thank you.
Yeah. Sorry if I don't. Yeah.